We're ready to start section 12.2, which is all about vectors, and in particular, it's about vectors that are in Euclidean space or n space, n-dimensional space. So we talked a little bit about Rn in the last section, our n space. Okay. For our purposes, n is almost always going to be 2 or 3. The rule is n has to be a positive integer. So most of the time we're going to be working in either 2 space or 3 space. In theory though, and this will happen, we could be in 4 space. Now it's difficult once we get into those higher dimensions to think about things visually because we live in a 3-dimensional world. So very often when we get into higher dimensions, we'll start thinking more algebraically and doing a little bit less with the visualization. Okay? But if a point in 3 space is just an ordered triple of numbers, a point in 4 space would be an ordered quadruplet. Don't know if that's a word, but it's a cool word, of numbers. Okay, but again, most of the time we're going to be working in either 2 space or 3 space. Now, some of you either have taken or will take or are taking linear algebra. In that class, you will address the question of what's a vector much more generally than we're going to do here. Because really, a vector is just an element of a vector space. And there are lots of different vector spaces, and vectors look very different depending on what space they're in. We're going to be working in Euclidean space, and there a vector is just something that has magnitude and direction. Magnitude is sort of a fancy way of saying length, and then we've got direction. So we can represent these visually as just an arrow, because an arrow has a magnitude. That would be the length of the arrow. That's going to be the distance from this point, which we call the tail, to this point that we call the tip. And of course, it has a direction as well, which we indicate by indicating that this is the tip, so that we're going up and to the right, not down and to the left. Okay, and so I can have arrows in 2 space or 3 space. Okay, can have them in 4 space too, but we're not going to worry about that right now. Okay, so what sorts of things might we use vectors for? Well, here are a few examples. Velocity. Okay. If this were a velocity vector, then the magnitude would be the speed with which an object is moving. So it sort of gives us a visual representation of speed. Something that's traveling faster would be represented by a longer velocity vector than something that's traveling slower. So sort of the length of the vector becomes a metaphor for how fast the object is moving. And then of course, if this was the velocity, the object would be moving in that direction. Now this is incredibly useful. If you think back to first semester calculus, one of the primary examples that we use for applications of calculus is a position function. And we know that the first derivative of position is velocity and the second derivative is acceleration. And we learn that velocity is different from speed because speed is just how fast you're going, but velocity indicates the direction in which you're going. But without vectors, in first semester calculus, we indicated the direction with a sign. And the problem with that is that there are only 2 signs, which means in first semester calculus, every position problem that we did had 2 and only 2 directions. You could go in the positive direction, you could go in the negative direction. Poof, you ceased to exist because you went in a direction that doesn't exist. Okay. So vectors free us up to use infinitely many different directions. So we can do much more realistic motion problems in this particular case. Okay. We can also talk about displacement. This is also linked to motion problems. Let's suppose I wanted to start at a point A and go to a point B. And these could be locations in either 2 space or 3 space. Now, if I travel from A to B, I might take a very circuitous path to get there. Okay. what I've just drawn is not a vector. That is not displacement. Okay. If I were to calculate the length of this path, which is something we'll learn how to do, that would give me the distance that I traveled if I took that path to get from point A to point B. That's also not the same as displacement. What displacement would be is just the vector that points from, whoops, let's try and draw that as a straight arrow, the vector that points from my starting point to my ending point. Okay. When I have that, when I name the tail and the tip of a vector like this, if I want to, I could name that vector AB, like so. Be careful, this is the starting point, this is the ending point. The vector BA would point in the opposite direction. Okay. But AB would be that. Now, the magnitude of displacement is not necessarily the same as the distance that I traveled. If I went from A to B along this circuitous path, the distance that I traveled is much greater than the magnitude of the displacement. But the magnitude of the displacement is the distance between my ending point and my starting point. Okay. And then the direction is just the straight line direction going from my starting point to my ending point. Okay. Another example of something that we can use vectors for is a force. Okay. If I apply a force on something, if I'm pushing on something, okay, how hard I'm pushing would be represented by as the magnitude of the force. That would be the amount of force that I'm applying. And again, when I draw that force vector as an arrow, I can represent the amount of force sort of metaphorically with the length of the vector. More force is going to correspond to a longer arrow. Less force would be a shorter arrow when I represent it pictorially like that. Okay. But then I'm also pushing in a certain direction. Okay, so forces have direction as well, and you're certainly aware of that if you've ever ridden your bike in the wind. If the wind is at your back, it's a lovely feeling because the wind is helping you along. If the wind is in your face, it's not a pleasant feeling because the wind is pushing you back and you have to work much harder. And I've actually ridden in a windstorm that was pretty bad where the wind was blowing horizontally and I was afraid I was going to fall over. So wind can be helpful or hurtful depending on both the magnitude and the direction. Okay, so those are some examples of things that we might represent with vectors. Let's talk a little bit about notation. Okay, if I'm trying to give a name to a vector, very often I'm going to assign a variable name to it. When I do that, I'm going to put a bar over it or an arrow, like so. That's important because as we go on through this semester, we're going to have lots of problems where we've got vectors and points and numbers. It's really nice to have a notational way of telling what this represents. I know that's a vector because there's a bar over it. If I didn't put the bar over it, that's what I would use to denote a number rather than a vector. Okay, now that's the convention if you're writing things by hand. If things are typewritten, the convention is that we put them in bold. So as you're reading your textbook, or if you're reading typewritten materials that I've created for this class, you're not going to see bars over your vectors, you're going to see them written in bold. We don't use that for handwritten stuff, because it's kind of hard to tell that I was pressing harder there. It's hard to show bold when you're writing things by hand, so we don't use that convention for handwritten stuff. Okay. Now, I could also give a vector in what we call component form. So if I have a vector and I call it 1, 2, 1 and 2 would be the components of this vector, and those are directions for telling me how to get from the tail to the tip. So if I wanted to put my vector here, okay, I would go 1 over and 2 up. This tells me how far to go horizontally, and the positive direction is to the right. If it was a negative 1, I would have gone 1 to the left. This tells me how far to go vertically, And the positive direction is up and the negative direction is down. So that would be my vector v right there. Okay. Now, if I happen to draw v in what we call standard position. Standard position just means that the tail is at the origin. So if I put the tail here, and I follow those directions, so I go 1 over and 2 up, notice that would put the tip then at the point 1, 2. I can say that v here is the position vector for this point, because when I draw v in standard position with its tail at the origin, it points to the point 1, 2. However, this vector, v, 1, 2, is exactly the same as this vector, even though this one is not in standard position. This one is in what we would call translated position. And there the tail is not at the origin. If this is the origin, the tail here would be over here at something like, I don't know, 10, 3 or something like that. Okay? So that would be an example of translated position. They're exactly the same vector. So the location at which you draw the vector is not part of its identity. This is actually a concept you're familiar with. I shall illustrate it. Hello, my name is Carla. I'm your math teacher. I am at a different location, but guess what my name is? It is still Carla, and I am still your math teacher. My identity didn't change just because I changed location. So where you put a vector is not a part of its identity at all. They can be drawn in standard position or in translated position. Okay. All right, let's suppose that I'm going to work in 2 space again. Let's suppose I have a vector and I want to put its tail over here at the point P, which I'm going to call 3, 1. And I want to put the tip at, 2, 4. We'll call that point Q. Okay. So we've said we can name this vector PQ, going from tail to tip. I want to now give it in component form. Okay. So I say, okay, if I'm starting at 3, 1 and I'm ending at 2, 4, I can see I'm going to have to go back 1, and it looks like up 3 in this case, so that would be negative 1, 3. Notice I can get these numbers by simply subtracting the components of P and Q. Okay. But the order matters. I'm not going to say 3 minus 2 and have positive 1, because then I'd be going to the right, and I can see this vector is going to the left. So if I'm subtracting, this would be 2 minus 3, which would give me the negative 1, and then 4 minus 1 would give me the 3. So when I subtract, I'm going to make sure that I'm subtracting the components of my ending point minus the components of my starting point. Now, in 3 space, we could do the same thing. Let's say in 3 space, I have a point 1, negative 2, 5, and a point Q, 2, 1, negative 3. So I could form the vector PQ. Now, it's a little bit harder to visualize that than just drawing it so nicely on this 2-dimensional whiteboard. I certainly could map it out, but I can also just remember that I'm going to get that by subtracting the value of my ending point minus my starting point. So it'll be 2 minus 1, 1 minus a negative 2, negative 3 minus 5. And I can think about that logically as well. If I'm starting at 1 and ending at 2, I'm coming forward. So I should be coming forward a positive amount. That's going to give me a 1. This will become a 3, negative 8. Excellent. Okay. There's one very special vector in each version of n space, okay, and that's the 0 vector. We denote it. This is the one time we're going to actually name a vector by just writing a number with a bar over it. There, the bar is very important because, of course, without the bar, this means 0 the number. This means 0 the vector. Okay. If I have the 0 vector, the magnitude of it is equal to 0. And what that means is that there's no unique direction. If I want to represent it graphically, it's like an arrow, but where the tail and the tip are the same. So there's no shaft to the arrow. I would represent that just as a single point. Okay. So if I've got 0 as my velocity, what that says is I'm not moving. So my speed would be 0. The magnitude of that vector would be 0. Okay. And there's no unique direction associated with that. But that's not to say that I can't think in terms of directions. If I'm not moving, I'm going 0 in that direction, and 0 in that direction, and 0 in that direction. So there's no unique direction, but I can sort of associate any direction with it that I want to, should that become useful. Okay. In component form, of course, depending on what space we're in, if I'm in 2 space, the 0 vector is just a pair of zeros as its coordinates, or as its components rather. If I'm in 3 space, the 0 vector is 0, 0, 0. Now, as we're talking about n space, we've sort of talked about Rn. Usually, as I said, n is going to be either 2 or 3. Our textbook views this as a set of points. And when we're talking about vectors, the book is going to use the notation Vn for vectors. Not all textbooks make this distinction. So in other classes, you may very well be talking about vectors that belong in Rn. Totally fine, considered acceptable. Our textbook is going to talk about vectors being in Vn. So when they say, hey, we're in Vn, you know we're talking about vectors. When they talk about being in Rn, they're talking about points. So that's just a notational thing that our textbook is going to use. It's not entirely standard. A lot of textbooks do that, a lot don't. You may catch me sometimes because the textbook we used to use didn't make this distinction. I might sometimes talk about a vector being in Rn, but I will try to respect the notational convention of our textbook and talk about vectors as being elements of Vn. Okay, that's our start to vectors.